Okay, so this is a term. It comes from base, sort of the jargon of the chemistry of buffers. They say they do a base challenge or an acid challenge. And I laugh because it makes me think a Tide Pod challenge, but it's not that. Okay, so what we're going to do is think about what happens to a buffer when you add sodium hydroxide to it or when you add HCl to it. Now, it could be any acid, it could be any base. Okay, so it doesn't really matter which one it is. But let's say you have 10 millimoles of HA, and it really is helpful to think about constant millimoles in these problems. And you have 10 millimoles of the conjugate base, okay? And you add 1 millimole of sodium hydroxide. So what will happen is the sodium hydroxide will react with the hydronium and shift the equilibrium to the right so that the concentration of the base goes up and we call it 1.0 because it really bugs me when it's not like sig figs are weird. All right, and then the concentration of the acid will go down by 1 millimole, so it's going to be 10.0, be 9, right, but minus 1.0. And then you could calculate those concentrations. If you do HCl, exactly the opposite happens. So if you add, let's say, 0.5 millimoles, just to use a different number, right? Then what happens is the concentration of A minus goes down by that amount. And the concentration of HA goes up by that amount. And there's like a real simple way to think about these problems. If you add an acid, then the acid form goes up. If you add a base, the base form goes up. I mean, this kind of makes sense, right? So if you add a strong base, the conjugate base goes up. You add a strong acid, the acid goes up. So, having said that, we'll talk about what a problem might look like and why it's important to think in terms of millimoles. So, a buffer solution contains 0.1 molar HAC and 0.15 molar NaAC, so sodium acetate. If 1 milliliter of 1 molar HCl is added to 25 milliliters of buffer solution, calculate the new solution pH. So in the process of doing this, we're actually going to calculate the change in pH, right? And then we're also going to calculate the new pH from that. So what we're going to do when we do this, we're going to work entirely in millimoles. So I'm looking for the pH, and that's going to be equal to pKa plus the log of, and then it's the concentration of the base, right? The conjugate base over the acid, like that. And you can say HA if you want. That makes it a little bit easier. Or you could stick with HAC and AC minus, like that. Now, what I want to do first is let's calculate the pH of this solution. And so that can be done, oh gosh, thought I turned that off. That can be done by going like this, 4.74 plus the log of, let's see, what do I have as my base? I wasn't even paying attention to my own question. Oh yeah, 0.15 and 1.0, so we're going to go ahead and do that again. And so I'll plug that in my calculator, although you might remember it from the earlier slide. So 4. Let me see, what is it? 916. Okay. So now what we're going to do is we're going to calculate it when you challenge the buffer. That means you're adding something to it to try to change the pH. So to do that, I actually want to do it in millimoles. So I'm going to say pH is equal to pKa, right? So that's going to be 4.74. Plus the log of, and now I'm going to do millimoles of the conjugate base. So I'm going to take 25 times 0.15, and that's 3.75. millimoles. I'm going to leave a little bit more room here. And then on the bottom, what I'm going to have is 2.5. That's my acid, because it's going to be 25, right, times 0.1. Sorry, you can't see me pointing at the screen. Oh my gosh, 25 times 0.1 here. So I'll end up with 2.5. Now my challenge that I'm challenging with is 1 milliliter of 1 molar HCl, so that is a 1 millimole challenge, right? Because 1 times 1. So, but which way is it going to go? Well, since I'm adding an acid, the bottom's going to go up by 1, and the top's going to go down by 1. And now we can calculate the new pH, or at least the change that's caused by that. Now you're probably thinking to yourself, that's millimoles, right? So this is why this is so cool, I think. Let's say, okay, I'm going to convert it into molarity, right? So what am I going to divide by? 26, right? Because that's my total volume, 1 plus 25. So I'm going to divide it by 26 milliliters. What am I going to divide the bottom by, right? 26 milliliters. That cancels out. So in reality, one of the super nice things about the Henderson-Hasselbalch equation is you don't have to always be using molarity. Sometimes it's much easier to deal with the actual number of moles. And you can actually calculate buffer pHs just knowing millimoles of acid and millimoles of base. Okay. So, having said that, we can calculate this value. Let's see, 3.75 plus 1. This is actually what I do every time I pause. I pause it a lot. 4.75. Oh, and I could do this one. Oh, sorry, I did the math wrong. So it's 2.75 divided by 3.5. So that's the ratio, 0.7857. That's this value here. So I'm going to go ahead and take the log of that. And then I'm going to add it to 4.74. I meant to pause this and not have you watch me do all the calculation, but there you go. Now it's 4.64. So that, well, I didn't check actually what the next digit was. 4.6, yeah, 4.64 is correct. 4.64 is the new pH. Okay, so what happened? Well, the pH went down, right? And that makes sense because I added a strong acid to it. But it only went down 0.3, not even, yeah, around 0.3 pH. It's not even quite that. But so that's the change in the pH. So the new solution pH is this. If you need the change in pH, you just need to calculate the initial pH and subtract those two. Okay? So anyways, that's how you deal with a challenge. You don't actually deal with the molarities at that point. Go ahead and do the problems in millimoles, and they're just working out. They work out a little bit easier that way. All right, so here's one for you guys to try. This is a base challenge, so you have to think about that a little bit. Go ahead and work it out, and then, oh yeah, sorry, I forgot the pKa. So the pKa is 3.17. And the way I got that is I just looked up Ka and then took the negative log of it. So there's the pKa. Calculate the pH of the buffer before the addition of the sodium hydroxide and after the addition of the sodium hydroxide. And I'll give you both solutions when you restart. Okay, so here's the solution. pH is equal to pKa plus the log of the base over the acid. Its pKa is 3.17. The log of the base, now it's 1 molar of each, and there's 10 mils, so that's 10 millimoles of each, right? So what that actually means is the pH before the addition of the base was 3.17, because before the addition of the base, it would have just been 10 divided by 10, which would have been the log of 1. So pH is equal to pKa, 3.17. Now, after the addition of the sodium hydroxide, so 0.75 times 2.0 is 1.5 millimoles. The sodium hydroxide, because I'm adding a base, sodium hydroxide goes up, right? makes the conjugate base go up, sorry, and the weak acid go down. So I calculate that ratio. It's basically 11.5 divided by 8.5, and I took the log of it. That comes out to 0.1313. And then I add that on top of the 3.17, and I end up with a pH of 3.30. So, just to confirm, like in our head, that did I do the calculation right? I added a base, the pH went up. That makes sense, right? I added a base, pH went up from where it started, so it makes sense that the calculation makes sense in terms of how the pH should have changed. Typically, when you screw these things up, you've changed the signs here, and it does the opposite of what you expect it to have done. So, I thought of one more problem. This is like the real problem I have with teaching online. I'm always thinking of additional problems for you guys to look at, so you have more to look at. It's kind of the value of online. So this is another kind of problem. So I just used the slide data from before, but I changed it to be a 25 ml volume of hydrofluoric acid buffer, the 1 molar, right, acid and conjugate base. Here's the difference in the question. It says, what volume of 1 molar HCl can be added before the pH changes by 1 pH unit? So this sounds much more complicated, but here's the deal. We're going to do it almost exactly the same way we've done the other problems. This is what I mean by that. We're going to say pH, right, is equal to pK. I'm going to write it up here because I'm a little short on space here. Can't get my pen to work. pH is equal to pKa plus the log of the base, right, over the acid. And it's the conjugate base. I don't know, I just don't like seeing it that way, but it's easy to write. Now, what we're going to do is this. We want to look at the pH changing by 1 unit, and we're adding HCl. So we're starting at the midpoint, like where these are the same. So the pH is going to start at 3.17. So I'm talking about a pH of 2.17, right? So notice how this is going to set up. It's going to be like this. It's going to be 2.17. The reason I'm doing that is because I'm adding an acid. If I was adding a base, I'd go to 4.17, is equal to 3.17 plus the log of the base over the acid. Now, I'm going to do it in millimoles, and you'll see why I'm doing it like this in a second. So this is going to be 25 millimoles on top, right? 25 millimoles on bottom. I should have probably put extra decimal points in there because I think that works out better. And then I'm adding HCl, and so the pH is going to go down, right? The acid form will go up. So the acid's on the bottom, so I'm going to say plus X, and on the top I'm going to say minus X. So this is the equation that we have to solve, and when you rearrange this part, you'll see why this is kind of neat. I know it's going down by 1, so it's going to be minus 1 is equal to the log of 25.0 minus x and 25.0 plus x. And now all I need to do is solve for x, and there's a lot of ways to do it. Just to save us some time, I'm going to go over to Wolfram Alpha. I was looking up the Ka values, so I need to go over to Wolfram Alpha and enter that equation in. Okay, so this is the equation entered, and then the value that I get for x should only have, yeah, 225/11. That's so helpful. 20.45, okay? 20.46, let's just call it that. So we're going to say x is equal to 20.46. And that's when it's going to drop by 1 pH unit. So this is right at the edge of the range of the buffer, right? So then what we're going to do is this. This is the millimoles, right? Well, this is actually the millimoles of the acid that I've started with. And so now I'm going to calculate the volume of HCl that I needed to add, right? And I'm going to take the 20.46 millimoles, and I'm going to convert it over with my molarity, and it's 1 mole per liter. So the moles will cancel, and it's 20.46 milliliters. So that's the amount you have to add in order for the pH to drop by that amount, by 1 pH unit.